Hey guys, and welcome to our first lesson on solving equations. In this case, solving one-step additive and multiplicative equations. Now, perhaps we've seen some equations before, so this may be a review, but it's really important that we understand what's going on behind the scenes and that we know how to write out our work properly so that when we're giving more difficult equations, we can handle them with ease and create good work that's easy to follow. So the first thing I might ask is, what does it even mean to solve an equation? Right? These are words that we throw around a lot. Solve the equation, solve the equation. But what does it mean? To solve an equation means this. Well, anytime you have an equation, you're going to have an equal sign, and you're going to have at least one unknown variable in it. You may have more than one, you may have just one. And to solve an equation means find the value, or values, for however many variables you have, such that the statement or equation is made true. Right? So in this case, we have n plus 6 equals 8. And we have this variable n, this unknown variable, and we don't know what number it stands for. And it could stand for a whole bunch of numbers, but in this case, there's only one number, such that if we substitute it in for n, makes this statement true. And perhaps you know that right off the bat, that number is 2, because 2 plus 6 is indeed equal to 8. So I'd say the solution to this equation is 2, n equals 2. Now, this was nice because we just got to kind of look at it, and I'm sure you could intuitively just tell. But I want to show kind of some thoughts about what's going on behind the scene. First things first. When I see this expression right here, I know that n plus 6 equals 8. Here's kind of what I envision in my head. All right, here's a very simple number line drawing where we have our unknown number n, and I know that if I add 6 to it, so I go 6 to the right on the number line, I end up with 8. So we immediately know that n has to be less than 8. How much less than 8? It's got to be 6 less than 8. And perhaps you just did this in your head. You said, okay, well, I'm just going to kind of undo that adding of 6. I'm going to go back down the number line to find out what n is. N is going to be 2. And how we kind of write this out notationally, perhaps you've seen this before, is I tend to say, well, we know that n is going to be 6 less than 8, so let's actually find out what 6 less than 8 is. That number happens to be 2. A lot of people also like to focus in on the fact that 6 and negative 6 add to 0, so you're kind of isolating your unknown variable n in this case. All right, not so bad, not so bad. Making moves. Ooh, so in our second example, 31 plus w equals 12. You can leave it as is. I often like to rewrite this as w plus 31 equals 12. Perhaps you already know what the answer to this is going to be. One thing I do know is that it seems that w is going to have to be a negative number. Because if I'm going to add 31 to it to get 12, well, w is going to have to be negative. I'll draw a quick picture again of kind of what I envision. Here's our unknown number w. I know that if I go 31 units to the right, I will end up at 12. So, what must be true about w? It's got to be 31 less than 12. I'm kind of going to undo that adding of 31 to get back down to w. Here's how I write this notationally, and this is a really key step that I really want you to include as well. This is using just intuition. What number is 31 less than 12? Well, I think that number is negative 19. So we'd say that w equals negative 19. And just to make sure, we might as well go ahead and substitute that back in. Is it the case that 31 plus negative 19 equals 12? Yes, indeed it is. Always a good idea to make sure your solution works, especially when the equations get a whole lot tougher. And so that's kind of the general theme here. In this case, we'll look at example number 3. I'm thinking that x has actually got to be greater than 84. Excuse me, negative 84. Because I know that x minus 9 equals negative 84. So if I were to draw this on a number line, here's my unknown variable x. I know that if I go to the left 9 units on the number line, I end up with negative 84. So what do I want to do? I want to find out what number is 9 to the right of negative 84. I'm going to add 9 to negative 84. I'm going to undo this subtracting of 9 right there to isolate our variable. I think that our unknown variable is going to have to be negative 75. I think that is the number, such that if we substitute it in here, it will make the equation true. So that's what it means to solve an equation, and here are 3 examples of one-step equations where all we had to do was add or subtract a number in order to find the solution, and I really urge you to have some sort of picture in mind when you do these. We can do these with fractions as well, that's no problem. Why don't you take a moment right now to try these 3 on your own, and then we'll reconvene. All right, in our first example, not so bad. I might just for myself rewrite this. Right side of the equation is h minus 41. I know that h is going to have to be larger than 46. It's going to have to be 41 larger than 46 to make this true. I think that the unknown variable h has to be 87 to make this statement true. 87 is the solution to our equation here because negative 41 plus 87 would definitely give you positive 46. All right, feeling good. In our second equation, nothing crazy here. We are just dealing with fractions in this case, but everything stays exactly the same. Our unknown variable y, if we add 9/4 to it, we're going to end up at 7/2. So what do I want to do? I want to undo that adding of 9/4 and go back to the left on the number line. So I'm going to take 7/2 and I'm going to subtract 9/4 from it. Some might say subtracting 9/4 from both sides of the equation. All right, now of course we just got to use our fraction skills and know that 7/2 can be written as 14/4. So our grand total should be 5/4. And 5/4 plus 9/4 will indeed equal 14/4 or 7/2. Our last example in this section. All right, ooh, this is an interesting one. Perhaps you already know that if we're going to take 17 and subtract a number from it to get 48, that number is going to have to be negative, right? 48 is greater than 17, so we're going to be subtracting a negative number here. What I might do first is this is what I envision. You might not have to write this every time, but 17 plus negative b equals 48. Let's go ahead and subtract 17 from both sides of this equation. Right, to figure out just something about negative b. Well, we now know that negative b has to be, let's see, 31. So if negative b is equal to 31, then I have to believe that positive b has to equal negative 31. Right, this sometimes is a conceptually hard thing to understand, but I hope that this makes sense. That if b is negative 31, negative 1 times b would be positive 31. And here's our solution. And I hope that this makes sense, that 17 minus negative 31 will indeed be positive 48. And so a lot of what we've been doing in these equations, especially in these steps in red, is we've been using our intuition and oftentimes our number line representations, but it really also is called the additive property of equality, which just says, and I'd write this down, if you have an equation, you may add or subtract the same number to both sides of that equation, and the equation will remain true. And that's kind of what we've done in all 6 of these examples. Awesome. So now that we've taken care of equations that require one step of addition or subtraction to solve, let's look at equations that require one step of multiplication or division to solve. So one thing I want to do is make sure that we're not focusing just too much on the symbols, that we know what's going on behind the scenes. So here is one way that I would represent this equation. 2m equals 24. All right. It's kind of like saying we have 2 m's here and that these 2 blocks for m are equivalent to these 24 kind of unit blocks. Maybe I'll even put an equal sign there. I should have done that before. And I've also kind of done this visually in such a way that then you can see that, 1m has to equal 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 blocks. So we know that the solution here is going to be that m equals 12. And perhaps you just already knew that just from looking at this, right? 2 times 12 is 24. But there are 2 notational ways that I want to show how to show the reader what you were doing. One is to say, well, if 2 m's are equal to 24, we want only 1 m. We want to divide this in half, right, to get just 1 m. There's 2 ways to divide this in half. One of them is to actually go ahead and divide by 2, right? 2 m's divided by 2 will give 1 m. 24 divided by 2 will give 12. Everything is good. But another way I really like to do it, and this is actually my preferred method, is we have 2 m's that equal 24. We only want 1 m. We want half of that. Let's multiply the left side of the equation by 1/2. 1/2 of 2m is going to be just regular m, 1m, and half of 24 is 12. Both of these yield the same solution, 12 in this case, but I also really want us to be able to visualize that situation right there. Okay. Similarly right here, I know that 6 times some number is equal to negative 42. If I want to know what that number is, well, I want to know what just 1k is. So I want to take a 1/6 of this side of the equation. Let's take a 1/6 of these negative 42. Sounds easy enough to me. Let's multiply by a 1/6. Let's multiply by a 1/6. And in this case, it should use some parentheses because things might get a little tricky with that negative sign. 1/6 of negative 42, 1/6 times negative 42, I hope we know is negative 7. So again, using just our intuition here. Yes, there are some notational skills that we use, and we use these symbols, but I want us to know what's going on behind the scenes as well. In this case, this is tough. We're saying that 3 times some number is 1/2. Well, here's kind of my representation of this. Here's my representation of a half. I'm going to use kind of a pie, if you will. That's 1/2. I hope you can agree. And I'm going to say that we have n, n, and n. So n, and n. Let's just pretend they're all completely congruent and equal. And my question is, well, what does 1n equal to? I hope it makes sense that 1n is equal to a sixth. 1, 2, 3, 4, 5, 6 n's would make a full 1 here. And so we know that n is equal to a sixth. The strategy, even though we have some fractions here, the strategy remains exactly the same. I don't want 3 n's, I want one of them. I want to have a third of those 3 n's. And what I do to one side of an equation, I will do to the other. Just take a third of this, take a third of that, boom. We find that n is equal to 1/6. This is one reason why I love using multiplication instead of division, because you can see that had I used division and divided by 3, there's nothing wrong with this, but this is one of those kind of awkward fractions right there, and it just makes me a little uncomfortable. So that's why I like multiplying instead of dividing. Can I get back there? Let's see how long that'll take. Oh yeah, way better in my opinion. A lot easier. Let's make some moves. All right, and hey, look at this. 5 times some number is equal to 17. Well, once again, I don't want 5 a's, I want just one of them. So I'm going to take a fifth of this number on the left, and I'm going to take a fifth of this number on the right. Right, so a fifth of these 5 a's will give you a, and well, a fifth of 17 is also known as 17 divided by 5. And you know what? That's okay as a solution right there. Sometimes our solutions are going to be fractions, and that's all right. And I definitely believe that if we were to substitute in 17 fifths right there, or 17 over 5, 5 multiplied by this number, the 5s will reduce to 1, you'll end up with 17. Aha! This number indeed makes that original statement true. So hopefully we're getting the hang of it. You can see also that there is a kind of general strategy here. But note that every single time we've had a number being multiplied by a variable, that number has been an integer, like 6, or 2, or 3, or 5. Also note to self, all of these numbers have been positive. For instance, if this out here had instead written as negative 3n equals 1/2, I would just visualize this as positive 3n equals negative 1/2. That's the way I think about it. In which case you're good to go, right? You can kind of multiply both sides by -1. Change the sign here and change the sign here, and you'll have a new equivalent equation. Likewise, you could always multiply both sides of this equation by -1/3, which happens to be the multiplicative inverse of that coefficient right there. And you would end up with the new solution to this new equation, n equals -1/6. So I just want to put on your radar what you would do if that coefficient were negative. Okay, let's finish up. All right, so these are some slightly tougher problems, but I think we're going to be all right. Here's a picture I'm going to draw for this situation. 2/3 times y equals 8. So here what I've got are 1, 2, 3 blocks, each of which represent 1/3 of y. And I'm saying that 2/3 of y, so I hope you can agree that this right here represents 2/3 of y, is equal to 1, 2, 3, 4, 5, 6, 7, 8. And our question is, what is the entirety of y going to be? Well, perhaps you can tell that the entirety of y is going to actually end up being 12. And I hope that that makes sense intuitively, just from looking at this picture. 2/3 of y equal to 8. 3/3 of y, all of y, equal to 12. And what I think we did is I think we took what we had and we said, listen, we've got 2/3 of y, we want to have 3/3 of y. Okay, well, how are we going to make that happen? And I want to talk about the notational step that we're going to take. And what I would say here is, all right, we have 2/3 of y. I want kind of 1.5 of what we've already got. I want 1.5 of what we've already got. I want a full y. So I might say, well, let's multiply here by 3/2. Why? No pun intended. Why would we do that? Well, because 3/2 times 2/3 times y, we're just going to get 1y. It's exactly what we want. And I hope you can see how this connects to the picture as well. And, well, what I do to one side of the equation, if I'm going to take 3/2 of this number, I'm going to take 3/2 of this number, and I hope that we know that 8 times 3/2 is equal to 12. So y equals 12 is the solution to our equation. And indeed, 2/3 of 12 is equal to 8. And in general, right, whatever our coefficient is on our unknown variable, we can multiply by the multiplicative reciprocal in order to isolate that variable and solve the equation. Aha! So in this case, in our second example, we've got 15 equals 5/2 times n. Let's multiply the right-hand side by 2/5. Right? We have 5/2 of m here. I want only 2/2 of m. I want to have just 1 m. I know that 5 times 2/5 is 1. So the right-hand side is going to become 1m. And if I'm going to multiply this number by 2/5, let's multiply this number by 2/5. And perhaps you already know what 2/5 times 15 is. That is equal to 6. Our solution in this case is that 6 equals m, or m equals 6. 5/2 times 6 equals 15. It checks out. It makes our statement true. It is the solution. And in our last example, we got a lot of fractions going on. We even have a negative number. You got two options. You can immediately just multiply this side of the equation by -1 and this side of the equation by -1, just so that we have nice positive coefficients on our variable. I hope you can see how these two are equivalent statements. But what I'm going to do is say, listen, I have my h here, and I want to kind of uncover and isolate that h, but it is right now being kind of muddled with by being multiplied by -5/4. How can I undo that being multiplied by -5/4 and isolate an h? Well, I'm going to ask myself, what can I multiply by here so that I end up with 1h? Well, and I'll make it clear that this is where the h is coming from. What number multiplied by -5/4 is going to give us 1? The multiplicative inverse of -5/4, namely -4/5. And what we multiply one side of our equation by, we will multiply the other, and we end up with 1h equals, well, whatever this product is. It's going to be negative for sure. 1 times 4 is 4. 2 times 5 is 10. So it seems like h equals -2/5. And always a good idea, especially with these complicated examples. Let's see if that's the case. If we were to actually substitute -2/5 in right here, would this be a true statement? Well, negative times negative is positive. We'd have 10 over 20, which is 1/2. Beautiful. It actually checks out. And this is all, what we've been doing here is actually part of the multiplicative property of equality, which says, and I would write this down, whenever you have an equation, you may multiply or divide both sides of that equation by the same number, and that equation will remain true. So that was our first intro into solving equations, and I really hope that we're understanding what's going on behind the scenes and not just focusing too much on the notation, and that we can explain our reasoning and why these work. So I hope you found this helpful, and I hope you enjoyed.